Okay, today we're going to look at the next unit, which makes the claim, or it's a theory, it's true, that r e to the I theta is actually r cis theta. And we're going to discuss this in the option. So what we're going to discover is that e to the x can be represented as 1 plus x squared over 2 factorial plus x cubed over 3 factorial. But we can't get to the yet. And the idea is that if you take x and replace it with ix, and you plug all the i's in there, and you don't need to write this down, it turns out when you square the i's and you manipulate this, you get 1 plus x squared over 2 factorial plus x to the 4th over 4 factorial plus, and then I take the odds, x plus x to the 3rd over 3 factorial plus x to the 5th over 5 factorial. It turns out, after we study Taylor series in the option, what was the option, what's now in the course, it turns out that an Euler discovered that actually this was cosine of theta, and you pull out an I, it turns out this is I sine theta. So we'll get to this, but right now for this small little unit, understand that whatever you see r e to the I theta, you know that's the modulus and that's the argument. And so this discovery really makes your life even more easier for just for mathematically, for manipulation of angle, multiplying complex numbers. And it's really helpful in physics. Complex numbers is really amazing. So and then let's see what's going on. So once again, you can copy this down. I'm erasing. Because it's now exponent, it kind of corresponds to those argument rules. So for example, if I multiply r e to the I theta 1 times r to e to the I theta 2, just knowing our rules and exponents, I feel like I need a new black pen. I think I got through this. You can just see, this is equal to, multiplying the moduli, and then you're just adding the arguments, and that's all we did. I'm afraid of the light. That's all we did with complex numbers. That was our claim. But yesterday's lesson, we needed to do all that, the FOIL and multiplying, cis times cis, and you had to do all that computation. Now, if we can represent it as exponents, we get to the same result. It's just much easier. So once again, if you see, so the question is, how do I write, this is 45? It's just literally, that's it. That's literally it. But now, you're just adding the exponents. Or for example, let's see. So if I see 7e to the, pi over 2i, the order doesn't matter. If you see this, you go, oh, you know what? Wait a minute. That's the modulus. That's the argument. You just know in your head. You know this is 7i. So once again, if we're going back, it's cis, pi over 2. Immediately in your head, though, you go, wait a minute. That's out 7. A rotation of 90, 7i. But this is the back and forth. If you're in E, it just makes it easier. Good. Is this true? Let's just verify. Yeah, 7 cosine of 90 pi over 2 plus I sine of 90 pi over 2. Yeah. And so cosine of 90, so 90, 1, 0, that's 0. And then the sine of 90, that's 1. Yeah, nice. let's move on. I'm erasing. What's the next interesting thing we can see? Well, what is re to the I negative theta? Well, we know this to be, that's the conjugate, correct? And let's just see, yeah, we can see that. It's r, cosine of negative theta plus I sine of negative theta. Now, last year we learned that cosine is even, so therefore this is cosine of theta, and last year we learned that sine is an odd function, so this is minus I sine theta, and if we let z equal a complex number, then I'm sorry, I apologize. If we let z equal our complex number, then what do we see here? This is the conjugate, which makes sense. It's just negative theta. What I'd like you to do on your own is, I want you to manipulate some of these. So I want to know what e to the I theta plus e to the negative I theta, and I want you to manipulate e to the I theta minus e to the negative I theta. I want you to see what identities you come up with. Once again, convert this into your cis, and then see what happens. When you add it, what happens to the reals? When you subtract it, what happens to the reals and the imaginaries? You'll get common results. It should be familiar to you. Now, the last thing they put in the unit, can you see over there? Let me move this over. The last thing put is kind of a cute little exercise. The idea is complex powers. Now we can raise something to the I power. So complex powers. And we have to remember, let's just remember that x is equal to e ln of x. And the idea is once we've raised something to the e power, now we'll be able to use Euler's rule. So, for example, 3 to the I. What is 3? What does it even mean? Well, we're mathematicians. We're taking everything to its extreme, not to extreme, but we're just exploring everything. And we really think about this class. We've raised numbers to positive integers, 0, negatives, fractions, radicals. Now we're raising it to imaginary numbers. Well, what are we going to do here? Well, we know that 3 is equal to e ln of 3. Therefore, 3 to the I is equal to e to the ln of 3 times I. Well, this form is Euler's number. So we can say that this is cosine of ln of 3 plus I sine ln of 3. And now we have a way of raising a number to a complex number. Here's something really freaky. Are you ready for this? This allows us to think about, what is I to the I? What is I to the I? Well, first of all, what is I? So the question is, I want to put Euler's. I want to use Euler's equation here. What is I? Well, I've been training you. Think about where I. How do we get to I? So you say, you know what? I is actually, it's, the modulus is 1, and the argument is 90. So technically, I, as Euler's number, is 1. I'm not going to write the 1 in. E to the pi over 2I. Right? That's I. Once again, the modulus is 1, and the argument is 90. That takes me to I. And so this becomes e to the pi over 2I to the I, which is e to the negative pi over 2. And it turns out, and this is awesome, right? Because it turns out that I to the I power is just a real number. I to the I power, what is it? Like negative 0.205. That's it. That's what I to the I is. You can put that in your calculator. Anyway, work on the exercises in the back of the unit. Just go through the computations, just because these problems show up on the IB exam. They like this stuff, but it's really intricate and it's tedious. But just go through, just recognize. Oh, you know what? When I see the cis or the cosine, this is just that. Argument, modulus argument, modulus argument. Good.